right, hello, good evening, good morning, good day, good afternoon, good night, wherever you are in the world again, and welcome to Freaky Physics. We have another stream today. We have a live stream. We have a live lesson today with CJ. Um, so we're gonna do more exam preparation for IB Physics today. All right, I'm gonna go into the lesson now, see what's happening. Oops, forgot my lab coat again. Hold on. Yep, let's put that on. All right, then I'm gonna join the lesson now and wait for him to get ready. Okay, so while we're doing that, let's get ready for all the materials we will be using today. I think we're doing paper 1 today, which is the multiple choice paper. All right, he's here. Let's see.
Hello, Mr.
Hello,
Dennis.
CJ. How are you today?
I'm good. How are you?
Doing good, doing good. All right. For today, if I recall right, we're doing paper 1, right?
Yes.
Okay. We will be doing the May 2021 paper for um. Okay, let me just get it ready here. All right, and of course, we are gonna use the same board as before. Um, okay. Oh, we're okay. That reminds me. Okay, we will continue instead. We're not doing it from scratch. We'll continue. We finished up to number 12 from before, right?
Mm-hmm.
So hopefully we can finish this today or maybe early on the next lesson. All right. So, okay, let me just share my screen here now. Uh-huh. Mhm. There we go. Okay. So this is where we ended last time. So we were just looking for the volume of a gas. So we were already at ideal gas loss. All right. So let's go to number 13 on the past papers. Okay. This question now is about waves. And okay, I think I'll copy and paste the question like this. Okay. Excuse me. By the way, how's the weather there right now?
Pretty hot,
Yeah.
but not as hot as like last week.
Good. Well, it's getting hotter here. Like
Oh,
I'm sweating like a pig now, and the AC is on already.
oh, yeah. In the morning, it's like even though my AC is really cold,
Mm-hmm.
it I can feel the heat.
Right.
Like I can tell it's pretty hot even though
Mm-hmm.
the AC is the same.
No, right? So, and thing is, back from where I'm from the Philippines, it's not
Mm-hmm.
well. I don't really come from the places that you would expect to be hot. Yeah. I live in a mountain town, so
Mm-hmm.
it's quite cold there, right? So I'm pretty used to the cold. So this is almost unbearable for
It's
me.
really bad.
Yeah.
Yeah.
All right. So, okay. So here's the question now. So you have an object performing simple harmonic motion as shown. The graph here shows the velocity v of the object as it varies with time t. We're looking for the displacement is x and the acceleration is a. Which of those graphs represents x and a as they vary with t? Okay.
Um, the variation of displacement with time and the
Mm-hmm.
variation of acceleration with time.
Right. Okay.
Okay, so that one's velocity over time.
Yes, this one's velocity over time, correct? Can I give you
When the
one hint?
velocity,
Can I give you one hint first?
yes.
Okay. The first hint is remember to find the velocity given a graph, or sorry, not to find the velocity, to find the acceleration given a velocity time graph, you just need to find the tangent at that point and find the slope of that tangent, right? All right, so that's the first hint.
Oh,
I'm not sure if that's very helpful. Second hint is again
I
the
thought
relationship between x and a. All right, go ahead.
I thought maximum velocity would be like zero acceleration.
That's correct. That's another way of
So
saying
I
it.
would assume it's the either the like you can look at A and C
Uh-huh.
where acceleration and time, like the second line, the
Right.
second graph.
Okay.
I
So
think
C
it's
and D are wrong already, right?
the oh
Right.
C and D. Oh, actually,
No, those are
oh,
wrong.
I
You're
was
saying
talking
that.
about the second like no, I'm saying that A and C, the second
Mm-hmm.
like graph
Uh-huh.
has like what I'm talking about.
Oh, A and C. Okay, for the acceleration, right? So
The
you're saying
second
so
for
you're
the
saying A and
acceleration.
C are correct already, right? So basically you're saying
Yes.
B and D are wrong. Is that it?
This is wrong.
Okay. You're correct so far. You're correct so far.
Okay, okay. Thank you, thank you. Let me pop off
Okay.
axis displacement. Um. Oh, okay.
Uh-huh.
Highest velocity, I assume. No, highest. It's highest maximum maximum acceleration is at the bottom. Maximum velocity is at the end.
Right. Okay, so what's the answer?
Does
A
that
or
mean
C?
maximum displacement?
A or C?
C.
Okay, correct answer. Your answer is C. The correct answer is A. Okay.
Okay.
Now, first
Why?
of all, your reasoning is correct. So at uh, Vmax, right? A is 0. That's the first one, right? So if you look
Mm-hmm.
at this, actually, with this particular reasoning, only D is eliminated because all A, B, and C are correct, like that, wherein A is 0 at T equals 0, right? So this is
Mm-hmm.
Vmax at T equals 0, right? So
Mm-hmm.
so definitely D is wrong. Okay. However, another thing here is remember you have simple harmonic motion. There's an automatic thing you assume here that A is directly proportional to negative x, right? Or if you turn that to
Mm.
an equation, that's A is equal to some value C times x, and then there's a negative sign there, right?
So it's opposite.
So they will always be in opposite signs, opposite sides. X
Mm-hmm.
and A will always be opposite each other. So if you look here,
Yeah.
uh, in A, that's what happens here. This is positive here. This is negative here. But they're the same shape, right? Similarly, negative here, positive here, but the same general shape. So that makes it the answer. B is wrong because they are directly proportional but not negative, right?
Mm-hmm.
So not negative, not following A is proportional to negative x. C is also not quite, right? Not exactly. Not exactly A proportional to x, right? Negative x. And of course D is wrong because um from this. Okay, so that's why D is wrong. That's why the answer here is A. Okay.
Mm-hmm.
Okay. All right. So again, just a quick one again. A is proportional to negative x, and the only set of graphs that does that is A. Actually, D also does that, but D is wrong because Vmax A is 0, and that doesn't happen. Okay. All right. Moving on. Okay. 15, 15, 16. Okay, I'll do the next two questions together. All right. Okay. These next two questions are still about sound, waves. Okay. So the first question is about sound. The second question here is about waves, in general. Okay. All right. 14. You have a sound wave frequency 1 kilohertz and a wavelength of 0.33 meters. What is the distance traveled by the wave in 2 milliseconds and the nature of the wave? Hmm.
Mm. I'll look at the formula booklet,
Okay, hold on. I'll get the
right?
form. Yep, you can check the formula booklet here.
Sound wave is longitudinal, so get rid of
Okay.
B and D.
All right, B and D are wrong. Okay, so far that's correct. Yeah, that's correct. So your answer is either A or C. Hold on. Let me get the formula booklet here. Energy here. Oscillations, traveling waves, wave characteristics. I'll just go the first three.
Is it C?
Is it C? Let's take a look. I'll just put that
My gut
there.
wants to tell me it's C
Okay. Or why'd you say C either way?
because times 1,
Mm-hmm.
like, it's just the same number, and then times 2.
Mm-hmm.
0.33 times 2. So it's just
Okay.
0.66.
All right. Now the I don't know the answer, and I don't want to consult the mark scheme. Let's solve this. Okay. So first of all,
Okay.
which formula do you use? Use this.
Mm-hmm.
Okay. Now you don't know the
Oh,
speed,
then I'm
but
already wrong.
you don't know the speed, but you already know the frequency in the wavelength, right? So from here, the
Yeah.
speed c will be equal to 0.33 meters times 1
Okay.
kilohertz. That's 1,000 hertz, right?
Mm-hmm.
And this already gives you 330 meters per second. Okay. Now the time I have to
Mm-hmm.
convert that, and then I have to convert that to seconds. That's in milliseconds right now, right? So the time here is zero. I'll just to say it in scientific notation: 2.0 times 10 minus 3 seconds, right? So how do you find distance? Distance is equal to time times speed times time. We know the speed. That's 330. Our time is 2.0 times 10 to the minus 3. That already gives us 0.33. Actually, if we can even simplify that, that's 0.33 already. 0.33 times 10 cubed, right? Times 20 times 10 to the minus 3. So that 3 and 10 to the 3 and 10 to the minus 3 cancel out. We're left with 20 times 0.33 gives us 0.66. Your answer of C was correct. Okay. All right.
Mm-hmm.
Okay. This you still need to solve using this, but there is no shortcut. You really have to solve it in this case. All right.
Mm-hmm.
Okay. Let's go to number 15. So you have two identical waves, each with amplitude x0 and intensity I, interfere constructively. Um, what's the amplitude intensity of the resultant wave?
Mm. Okay.
Okay,
Constructive. That means they add on to each other.
that's right.
Amplitude is double,
Okay, so
so get rid of A and C.
A and C are correct. Correct. Okay.
What is intensity?
Okay.
I'm just gonna guess B, because why not?
Why not? Okay. Good guess in all honesty, but the answer is D. Okay.
Okay. Why
Why?
is it times? Why is it?
Okay.
Yeah.
It's actually still here. On the data booklet stuff
Oh, it's
here.
squared.
It's squared.
I equals.
Intensity is proportional to amplitude squared. Okay.
Hmm.
I'm gonna copy that again into here, and I'm gonna put some annotations on what these formulas mean. Okay. Um. All right. Let's put this here. Okay. So just to annotate, this means the first one is the amplitude squared is gonna dictate how much I is. So I is proportional to amplitude squared, right?
Mhm.
Okay. The second one, I here, okay, this is I is proportional to distance from source squared. That's what the x is. This last equation
Mm.
here is for this is Malus's law, which is for polarized light. Again, polarized light. Okay.
Mm.
Okay. So the answer here, again, let's just mark that, is D. This is correct. And then using I is proportional to A squared leads straight to that. Okay. All right. Let's go to the next number. Excuse me. So
Okay.
we have here for the next question three quantities used to describe a light wave. Let's put it in now. Okay. So the three quantities here, let me read it out while it's pasting. So the three quantities are frequency, wavelength, and speed. So, um,
Mm-hmm.
okay, I'm not going to read the rest of the question until we get.
C equals F lambda.
C equals F lambda is going to be useful here. Now, the question is which quantities will increase when the light wave passes from water to air? Water to air.
Oh, oh. Wait. Wavelength decreases
Mm-hmm.
because it goes faster.
It goes faster in air, right?
Mm-hmm.
So your answer is.
Frequency increases.
Mm-hmm. Okay.
I think get rid of two. So C out.
Sorry, get rid
C
of
and A and D. I think it's B,
B.
personally.
Okay. Um, your answer is B, the correct answer here. Let me think about this real quick. Uh, it's not B. It is C. Is the correct answer. Okay. Now the
Wavelength
idea,
increases.
yes, because here you know that from water to air, speed increases, right?
Mm-hmm.
Okay. All right. So definitely speed is correct. Now the thing here is frequency. Once the wave is produced, I'm gonna say it like here. Once the wave is produced, it doesn't say once the wave passes through or whatever. It's produced, right? Once the wave
Mm-hmm.
is produced, its frequency doesn't change. Okay. So again, once a wave is produced, its frequency does not change. It stays as is. So in other words, this is constant. Okay. Then
Mm-hmm.
as you said, speed is equal to lambda wavelength times frequency. Since this increases, c increases, but this is constant, then that means the wavelength must also increase. Hence, 2 and 3. Okay. All right. So again,
Mm-hmm.
key takeaway here in this question is that the frequency is doesn't change once the wave is produced. So once it's produced, it passes through whatever, its frequency remains the same. Okay.
Mm-hmm.
All right. So, right, let's move on to the next question here. Interesting question we have here. We now have harmonics on this next question.
Mm-hmm.
All right, and then the question after that's going to be about electric charges. Right, so the question here now, you have a pipe whose length is L. It's closed at one end. Then you have a second pipe open at both ends and has length 2L. Sorry, that didn't get copied. I'll just write that there. 2L, right? So what is the lowest common frequency for the standing waves? I think this one's a little bit tricky, even for the better students.
Mm-hmm. Speed of sound, air dawn. Hmm. What's the lowest common frequency?
Mm-hmm.
Can I look at the equation?
Oh, sorry. Yes,
Fine.
of course, of course. Hold on. Which equation are we
So t equals
using?
1 over, never mind.
I don't think that equation is in the data booklet for this, but I'll put the data booklet
Oh, is
equations
it?
in here
It's the
because this is about harmonics, right?
um, first harmonic is like, oh, it's like 2, like,
Mm-hmm.
there's like a 357, which is the open on one side.
Yes, correct.
357 over 2,
Don't
like
forget
like
one.
3
One,
over 2.
yeah. But don't forget that it also has one. Okay, so what I would
Oh,
do
one three
again,
five seven.
1357, all odd
Mm-hmm.
numbers. Okay, that's for the half open tube, right?
But now the normal open is it just 1 2 3? It's 1 2
That's
3.
right. That's right.
Um. Oh, what is the common frequency
Okay,
for both of them?
yeah, for both of them. What's the first common frequency that they have? For example, okay, never mind what I was thinking.
Hmm.
All right. Okay, I'll give you. I'll just do what you said. Okay, I'll just draw here what you said. One is half open, and then the other is open on both sides, right? And we know the
Hmm.
lengths. This is L, and this is 2L, right? Okay. Now, what else do
Yep.
we know? What else do we know? You said something earlier. It's about the equations to use. This is gonna be N. The length would be equal to
Hmm. And
uh
wait.
the wavelength, right? Over some number N, right? So and
Hmm.
then have or better yet, you know how I do this? It's a lot easier if I draw everything. So just to help you out a bit, this is how I will draw it.
Wait. What is n?
Okay.
Number of
N
wavelengths.
N would be the number of
Harmonics.
harmonics,
No.
the nth harmonic. Okay. Now
Oh, okay.
this is the way I would normally do it. So for the half open tube, it's gonna be easier for you to know that this is gonna be a node and this is gonna be an antinode, right?
Yeah.
Okay. So if you draw that, you can already see that this is gonna be um this L is gonna be like 1/4 of the wavelength, or it could be 3/4.
Hmm.
Okay, 1/4 or 3/4 or whatever, as you said earlier, right? Okay. The second one, the open pipe, I'm gonna draw it again, and this time I'm gonna draw an antinode and an antinode, right? So the first easiest antinode I can make is that. So if this is now, let's do this as 2L. This is also equal to half of the wavelength, right? And then you can do or
Hmm.
one wavelength or three halves wavelengths, etc. Right? Okay. Now
Yeah.
the trick here now is you're gonna have to find um okay, what is the most common
The
frequency?
number
Okay,
of waves.
yeah. In this case, you really want the frequency, but remember because it's a common frequency, that also means it's a common wavelength, right?
Hmm.
Ah, okay.
So
So
the wavelengths equal the same. So we
yeah.
put the two equations on both sides.
Mm-hmm. Exactly. So lambda same, right? So once we do that, how do we solve it further? So once we do that, we're just gonna have to write here. We'll rewrite the first one. So this is gonna be lambda is equal to uh 4L over n, where n is 1357 for the first one, right? Okay, and that's also
Hmm.
gonna be equal to for the second one. What's lambda equal to? So that's
Wait.
gonna be. Go ahead. 2L
You did
or
4L because it's a quarter wavelength, right?
yes, yes.
So it's 1/4 lambda equals L over N.
Mm-hmm.
So you multiply by 4.
Mm-hmm. But
Okay.
all right. And then for the second one, I'm gonna use another letter for now, M, because they're not always gonna be the same, this N and this M, right? So what cancels out? This 4L and this 2L cancels out. That leaves you 2. So 2
Wait,
over N.
how'd you know it was 2L?
Hold on.
Because of what I said about
Yes, it's this part.
one. Yeah,
Okay.
okay.
All right. So we're left with 1 over M, or finally, N over M is equal to 2. So that's the smallest possible ratio. So what's the smallest possible ratio we can get for N and M to give you 2? 2 and 1, right? So that could be 2 over 1, that could be 4 over 2, whatever. But since we're looking for the smallest one, we're going to use this. So this is going to be 2, and this is going to be equal to 1. So finally, 4L over 2 is equal to 2L over 1. That cancels out with that. That still gives you 2. So let's take a look at their choices now.
Wait, sorry. When
Okay.
you take out, um, when you took away the 4L and the 2L,
Aha.
that leaves 2.
Mm-hmm. That leaves
So
2.
lambda equals
So L
2
equals L.
over,
L equals L, right? So in other words, any length L will work. And because any length L will work, what's our answer here? Our best answer
D.
will now be D. Okay. Now, that's the long way. There is a short way. There is a short way.
Mhm.
Okay. So that's the long way with the solution, right? Uh, Short way is still going to rely on the diagrams. So if I'm going to draw two of those other pipes, wherein we have a node here and an antinode on the opening, and a node antinode opening like this again, this looks exactly identical to our problem of 2L. This is L and L with the open pipe. This is two closed pipes, right?
Mhm.
And this is one open pipe. So you see, what no matter what the L is, even with this reasoning here, it no matter what L is, it will work because these two are basically equivalent to each other, right?
Mhm.
Basically equivalent. So the answer, nonetheless, either way, is still D. Okay.
Mhm.
All right. Of course, the other part of that is after you find the wavelength, you use C equals lambda F to find the frequency, but that's exactly what the formula is anyway. Okay. So, okay. All right. So I want to discuss the short one again. Yeah. So the short one again is this shortcut here relies on you seeing something, some sort of pattern. The pattern is if you copy the shorter closed pipe, you make a copy on the other side, and then you put them back to back like this, you're essentially gonna get the single long open pipe, and that should
Yeah.
get it. Okay. All right. So let's move on to the next question. So you have two charges. It's now electric charges. You have two charges, Q1 and Q2, each equal to 2.
Wait, is it
Now,
Dennis?
yes.
You said it was open on one side, but then wouldn't you only need one? Why draw two?
Okay. The
Is it
reason,
because the open was open on okay, is it because the open is 2L,
yeah,
but the close on one end is 1L?
yeah. So again, let me
Oh, okay,
read.
that makes sense then.
Okay, that makes
Yeah,
sense now, right? So again, let's just draw that.
yeah.
This is L, and then this is L,
That's 2L.
and that's 2L. That's exactly the setup here, and that's exactly the setup
Hmm.
here, right? Which is the same equivalent as one big long open pipe like that.
Yeah.
Okay,
Hmm.
same setup. any L will work, right?
Yeah.
Okay. All right. So let's move on. Continue here. So now you have two charges. Let's zoom in a bit. You have two charges, Q1 and Q2, each charge being equal to 2 nanocolumns, and they're separated by a distance 3m in a vacuum. What's the electric force on Q2 and the electric field due to Q1 at the position of Q2? Now, to better answer this, it would be better to draw the problem first.
Yeah.
Okay. Put do I need to put in? I think I'll need to
Do
put in
I
the
do
formula.
the two equation one, like the one where it's like
You could.
rearrange the second and the fifth one?
Mm-hmm. Now
Mm.
it's okay. Here's the data booklet formulas. Which one is going to be useful for the first part
F
and the
equals
second part?
F equals EQ and F equals KQ1 Q2
Mm-hmm. So
over
these
R
two.
squared.
So these two would be useful. Okay. All right. So what's the
Mm,
electric force?
wait, what is E exactly? E is
This E is electric field strength.
that's what we're finding?
That's you're finding that here, right?
Okay, okay. So E equals KQ1 over R squared?
Mm-hmm. So yeah, exactly. So
Okay.
K Q1 over R squared. Okay.
And so 2 and C. So it's the constant is it 8.99
The
times
K, yes, yes,
I don't
correct.
know.
So K is equal to 8.99 times 10 to the minus 9.
Times 2 times 10 to the let me look to the negative 9
Okay.
times 2 times 10 to the negative
Sorry,
9.
not that, not minus 9. This is positive 9. So let me redo
It's
that.
NC, is it?
Uh-huh. Okay.
But it's
Um,
little n.
yeah. So, it's not what? The answer now is neither C or D, right?
Mm-hmm.
Okay, so neither C or D because these are correct.
Wait, why is it
Answer.
not negative 9?
Um, okay. Remember that the electric field, let's just put that formula in. That's equal to, I'm just gonna write 8.99 times 10 to the 9. That's your K, right? Okay,
Mm-hmm.
and then your Q, your charge is 2 nanocolumns, and nano is 10 to the minus 9. So
Yes.
that cancels out. Okay, and then of course we have your
Yes.
R squared. What's your R squared? We don't really know, right? Oh, we
Mm-hmm.
do. That's gonna be 9 square meters, right? Okay. Now
Mm-hmm.
this K here, this is in the data booklet anyway. This is in the unit Newton meter squared per column squared. So this is already in meters. So in other words, this meter just cancels out eventually, right?
Mm-hmm.
Right? So what's left over? We now have newtons per column. And that's going to be basically this is approximately 9. So 9 over 9 gives you 1. So 1 times 2
1,
gives you 2.
2.
And C.
Wait.
That's your
How
electric field.
did you cancel out the square?
Oh, okay. If I'm going to write it out in full, just so it's easier for you to see, yeah? I'm going to write this part, the first part with the unit. This is Newton meter squared per column squared. This is uh this is already column, right? So this column and that column cancels out. We're left with
Oh, I
1.
see it.
And then this meter squared and this meter squared cancels out. We're left with newtons per column. All right.
Mm.
So that's the electric field. How about the force? We use the formula just as we see there, right? So to make this easier, your K, you can just estimate that to be 9. Okay. You can already see what you need to do. There's a shortcut. You don't even need to use this anymore. Oh, sorry. You don't need to use this anymore. You can just use this because you already have your E, right?
Yeah, I do.
Okay.
So
So all you have to do is multiply that E by the other charge.
two.
And the other charge is also 2.
Other charge is 2.
Yeah, 2
So
nano
it's just
columns, right? So what's your answer now? Is
um
it A or B?
I mean it's to the -9.
Mm-hmm.
So I think it's A.
All right, so correct answer is indeed A. All right,
Yeah.
great.
Because no like 4 times 10 to the -9 is 4 times 10 to
Mm-hmm.
the -9.
Mm-hmm.
Exactly. Or
Exactly.
2, I mean.
Yeah. So, or another way of thinking about it, I have 2 newtons per column, and I'm gonna just multiply that 2 newtons per column by 2 nanocolumns. So that gives you 4 to the minus
Yeah.
9. Okay, great. I think that's clear. So we can move on to the next question.
Mhm.
Okay, I
Yes.
remember discussing this with you before. But this is a little bit of a different application from what we did. Okay.
Mhm.
Okay, just wait. It's pasting. All right, so here we go. Let's zoom in a bit as well. Okay, so okay, in this case we have two conductors. Basically, the voltage to I graph or characteristic is put here, the characteristic graph. Okay. When the conductors are placed in the circuit below, the reading on the ammeter is 6 amps. What is the EMF of the cell? This is a bit tricky, but all the relevant concepts are simple.
We use the EMF equation or no?
No, you don't. Because you only use that if you have an
Mm.
internal resistance. In this case, you don't
Mm.
have internal resistance, right?
Mm.
Okay, so which one am I copying? I think I'll copy this. Okay, so here's the data booklet information. Okay.
Something about the Kirchhoff's circuit laws.
No, you don't even need Kirchhoff's circuit laws here.
Oh.
Okay, I'm gonna give you a hint. Go back, go to this particular bit first. What kind of connection do
Mhm.
you do here? What kind of connection do you have between the two resistors? Is this a series or
Parallel.
parallel? Okay, parallel, right? So which formula do you use for parallel resistors?
1 over R
Okay,
equals, or 1 over RT equals 1
okay,
over R
right? So you have to
S
use this,
plus 1 over R T.
right? However, you don't have the resistance, right? You don't have the resistance.
Mhm.
How do you find the
I know it's
resistance?
split between the two.
Uh-huh. Now here's the thing, you're given the current, right? And this is a
We're also given the volts.
uh-huh. You can find the
Oh,
volts
oh,
from the
6.
current, right? So for
Yeah,
S,
it's 5 volts.
okay, for um okay,
When it is 6 amps, it is 5 volts.
okay, so in this case for S, right? How about for T? At 5
When it
amps,
is 3 point
at 6
S. Oh,
amps,
wait.
5 volts, right? And then what do we have here for the other one?
T is like
So at
A
6
equals like
amps,
3.8.
what do we have your voltage here?
Um, oh, 6. No, wait, that's 8. Sorry,
That's
I
8,
couldn't see
sorry,
it.
that's at 8. Yeah. So 8 volts, right? So think about it this way. These are resistors and these are the current and voltage values they have. So what's the resistance of S? What's the resistance of S equal to?
Hmm.
And what's the resistance of T?
Okay,
You
wait.
just use which formula now?
The third one.
Third one.
The
Ohm's
one
law.
after Kirchhoff.
Okay. Ohm's law, right?
Mm-hmm.
Okay. So
Mm-hmm.
let's solve. This is Ohm's law.
R
What's the
equals 5
resistance
over
of
6 and
S?
R equals
Okay, 5 over 6.
3/4.
I'm gonna keep it in the fraction. Okay. V equal, sorry, V
Mm-hmm.
over I. 5 over 6. And then RT would be 8 over 6, right?
3/4.
Is
Oh,
it
8/6.
8 over
Wait.
6, right? That's 4
Yes.
thirds. All right. But we'll keep it like that. Okay. Now that you have that, what's gonna be your R total? Now, the
1
reason I'm keeping it
over.
as fraction is it's gonna be easier to work with.
Mm-hmm.
Since they're already fractions, you don't have to do 1 over a value. You just flip the fraction over, right?
Oh,
So that's gonna be
so it's 6/5
6 over
plus
5
3
plus,
quarters.
yeah, or 6 over 8. Or if you prefer 3/4, okay, let's put 3/4 in here. 4 thirds, right?
Oh, sorry.
Okay, it's okay either way. Um, you can still solve it either way. So
Or
this
we
is
could change
going
it
to,
to 20.
okay, that's gonna be something over 20, correct? So what are we gonna do now? So 4 times 6, that's
Wait.
24 plus 15, right? And that's gonna give you
39/20.
39 over 20. Okay, so that's the 1 over RT, right?
Mm-hmm.
Okay, now finally, we're looking for the EMF. So, in other words, we're looking for the voltage.
Mm-hmm.
So, what's the voltage? We now know, okay, we know the current is still 6 amps, right?
Mm-hmm.
Mm-hmm. Um,
So, R divided by, no, I divided by R equals B.
mm-hmm. I over R equals V. Your I is 6.
Therefore, 6
Your 1
divided by
over R
39 over
is
20. Wait, can I just call it
39 over 20.
2?
Okay. Yeah.
Just call it 2. So it's
Mm-hmm.
not 3.
Mm-hmm.
Can I say it's 4?
Yeah. Uh-huh. And what's your V? We're looking for that, right? Yeah, that's gonna give us what?
Mm-hmm.
Approximately what? Now I'm gonna tell you that this is not quite the right
4.
approach. Not quite the right approach, but it would still give
Oh,
you a reasonably close answer.
is it not? Oh, then it's not A.
Mm-hmm. This is approximately 12, right?
Uh,
Why? Because this is gonna be
oh, wait, actually.
approximately 2, right? So 2 times 6 is approximately 12. So which one's the
Wait,
best
wait.
answer?
I over R?
Uh-huh.
Wait, it's not I over R. It's R times I.
V equals IR, right? Okay, so there's a mistake, I think.
IR. Oh,
V equals IR.
sorry, I didn't see it.
Okay. So V equals
Yes.
IR. So it's gonna be 6 times what's your R? 20 over 40, right? Or 39, which is approximately,
Basically 2.
this is basically one half, right?
2.
So that,
Oh,
because remember, your 1 over R is
wait.
2. So this means RT is equal to 20 over 39,
Oh,
right?
we flip it.
Okay, you have to flip. So this is
Mhm.
approximately 3. So what's the best answer?
Wait. What? You did 20 over 39.
Mm-hmm.
Yes. It's you, it should be A,
Should
but
be A,
you
right?
make it sound like it's not
It's
A.
not exactly A. So that doesn't quite sit well with you. It doesn't quite sit well with me as well, right? Okay. So where's the mistake? It's a very tiny mistake. This is I'm just telling you now, this is a little bit of a challenge. Okay. However, it's actually easy to see once you spot the mistake. The answer, by the way, is A, even if you guessed it's A. So this is the correct answer.
Oh,
Okay. Now, the reason why we don't get the correct answer of 4 is because we didn't use the correct value on the graph. right? So the reason here is I'm just gonna redo the diagram again, but not the graph. We'll go look at the graph again later, right? So if we redo this the circuit diagram given to us, we know that the total current is gonna be 6 amps. That's the total current, right? It doesn't say that that's the current through both.
Mm-hmm.
This one here is gonna be 6 amps going this way, right? Okay. Now we're gonna look for a
Yeah.
particular voltage wherein if you add their currents, it's gonna be 6. That's what you actually look for here. So I better change colors. Okay, so this is gonna be 6 amps. And that means whatever the current here, let's say this is gonna be I, the current here will be 6 minus I, or the other way around. This is 6 minus I. They're not necessarily equal, right? Because one of them would have a bigger resistance. However, you can already see here on the graph which possible values of V. You look at the value V, wherein if you add their resistances, they add up to 6. Sorry, you add the currents through them, they add up to 6. So here, this is 6. This would add up to 12, right? So should be somewhere here. Okay, 6, 4, 3, 3. Okay, this is going to be helpful. The current here is 3 when the resistance is, when the voltage is 4, right?
Mm-hmm.
So this kind of works because here at 3, they intersect, the two graphs intersect. So in this particular case, the two resistors, RS and RT, are equal, and that's 3. Okay? Now,
Mm-hmm.
once you use this, you don't even need to solve. Boom. Answers 4 already.
Mm-hmm.
You get it?
Uh, why is it? Why though?
Okay. Uh okay, I'm gonna teach you a technique. This time it's a technique for solving using the answers. You're given the choices, which one makes sense, right? But it still goes to the fact that it still goes back to this fact that the two currents must add up to 6, right? So parallel,
Mm-hmm.
I s should be plus I t should be equal to
Oh, so
6.
they share the currents.
Yeah, so they share the
Mm.
current, and when they add up, it should be
Oh,
6,
that makes sense.
right? So all you
Mm-hmm.
have to do now is look for the current, wherein if you add them up, it's 6, and then see what value of the voltage is. This is an easier solution, in my opinion, rather than this very long, winded one, right? Okay.
Uh,
Again, honestly, number 19 is a difficult question in terms of trying to solve fast. It's easy to do if you know what
yeah.
you're doing, but with a time limit, there should be an easier way to solve it, and that's the easier way. Okay. All right.
Mm-hmm.
I guess we're now at 20, so we are 2/3 of the way through. Okay, for a real cell, let
Mm-hmm.
me read that up now. So for a real cell in a circuit, okay, let's do that again. For a real cell in a circuit, the terminal potential difference is at its closest to the EMF when the internal resistance is much smaller than the load, a large current is flowing, the cell is not completely discharged, and the cell is being recharged. Okay, I'm going to tell you now. Two of those you can eliminate right away.
Wait.
If you know what you're looking for.
A large clone. Wait, no. The cell is not completely discharged. Cell's being recharged. Potential difference is like the electron, like
Mhm. Now, I would
the
almost
voltage
say,
of the electron in the that's being moved.
uh-huh, that basically when you see potential difference,
Okay.
it's just voltage. Okay, just voltage.
Yeah, voltage in the current,
Now,
like
voltage of the
in the
battery.
circuit. Oh.
That's the voltage of
Potential
the battery.
difference is voltage of the battery. Okay.
No, terminal potential difference is the voltage of the battery.
Terminal potential difference.
Mm-hmm.
Okay. Oh, I didn't see the terminal.
Okay.
Okay. Um, a large current flows into the circuit.
Mm-hmm.
Is not.
Okay. Okay, I'm gonna
Did I
ask.
already mess up?
Okay, I'm gonna ask you something. I'm gonna ask you something. Does
Okay.
the terminal potential difference basically depends on the internal resistance. That's all you have to remember here. So the terminal PD
Hmm.
depends on internal resistance, right? Depends
So the
on
more
act.
there is, the less resistance.
Okay, internal resistance and load resistance. Now, why did I say that?
So
Because this
the
is actually in the formula booklet. In the formula booklet, it says, where is that thing? That's 5.3. It's this. Okay. So, do you see in the equation anything about the cell itself?
mm, the EMF
It's just the EMF, but it doesn't say
and
about
the small
anything
r.
about the quality of the cell.
No.
No. So, which one can? So, um, EMF could still depend on any of these, but basically not dependent on the cell itself, right?
Hmm.
At least in the formula. So, using this idea that it's not dependent on the cell or what's happening to it, what can you eliminate?
C D.
C and D cannot be the answer. Okay. All right.
Mhm.
I'm going to give you a clue. A and B are opposites of each other, more or less.
Mm.
More or less. So, time to guess. Which one do you think the answer is? If you're not sure, you can guess first.
B because I thought if you like say like it's I think it's like friction where
Mhm.
the faster you move, the less friction acts on you. Or
Okay.
like the faster something's running down,
Well,
there's more
actually,
of it,
that's
but
actually that's
it
actually a
is less.
very good analogy, but the that
Oh,
analogy actually leads to A.
oh,
Okay,
actually.
let's do that analogy. I like that analogy. So let's compare this to friction and motion, right?
Mhm.
Okay, versus what's this? Uh, internal resistance, right? Internal resistance and terminal PD, right?
Mhm.
Terminal PD. Okay, so if we compare these two, what's the analogy here? More more mass, right? More mass
Mhm.
means less affected, right? So
Yeah,
in motion, the thing that makes things move is mass, basically. So or something like that, right?
yeah.
Now, uh, in circuits, what's the most important component of a circuit? There are two. It's the power source and the resistors, right? In this case, we'll look at the
Mhm.
resistor. Bigger external load, bigger load means less affected by internal resistance. Okay, let's add that. Let's add the terms here. Less affected by friction, right? And then bigger load is via the acceleration, right?
Mhm.
Okay. Now the bigger load means less effect from internal resistance. Okay. In other words, it takes up more. The bigger load will use up more of the actual potential difference compared to a smaller load. Again, it's simply because of this again, right? Um, okay. I think I gotta do a bit more explanation here, but that's why the answer here is B. Okay. Oh, sorry, not B.
Mm,
The answer is A. Okay. The
right.
answer is A. Okay. The smaller the internal resistance compared to the load, the smaller its effect. Just like the same amount of friction would have a bigger effect on a small mass than a large mass. Okay. So yeah, okay, new analogy. Thank you, CJ, for giving me that. I like that analogy.
So
All
thank
right,
you.
but you understand, you more or less understand that.
Yeah.
Okay, so if you're not really totally convinced, you can always go back to this formula here. We can do that later because I don't think we have enough time to explore that through the formula.
Wait, so big R is load resistance.
Yeah, big R is load. I'll just note
Mm,
that here. This is the load, and this is the wait, I'm oversaturating with blue. I'll change the color. Okay, I'll change that to orange. So from here, R is load, small r is internal. Okay, internal. Then load for big R. All right. Okay. I guess that's it for this. Any questions?
no.
No. All right. Oh, it's already 7. So, okay, we have 10 more questions to go through. Our next meeting would be, if I'm not mistaken, tomorrow, right? Yeah,
Yeah.
tomorrow. All right. Exams are coming up soon.
Very. Yeah.
Yeah, I'm also pretty worried about this exam because not for me, but for my students. But let's see how they go. All right, so okay, we'll
You'll do
continue.
fine.
We'll be fine. Hopefully, we'll be fine. But anyway, so that's it. We'll end today here. So tomorrow we'll continue with number 21. Hopefully, we can finish. Right?
Okay. Sure.
Okay. So with that, we can end here. Anything else before we end?
Wait. Okay. Sorry, I was like wondering
Uh-huh.
if I booked 2 hours. Wait. Oh
I'm
no, my time is just weird. It says I have a lesson starting in 2 hours, but
okay. I'm
it
gonna refresh that
it's
as
already
well.
been 2 hours.
Oh, okay.
Yeah, I
That's
don't
kind
know.
of
It said
weird.
6 p.m.
Tomorrow.
Okay, okay, okay.
Yeah.
Okay, tomorrow.
We
That's
have
good.
6 we have 6 to 8 tomorrow, right? Yep.
6 to 8. Yes.
All right.
Okay.
Yeah. All right. So we'll hopefully we can really make use of the time. So tomorrow, 2 hours. I will see you then. Okay.
Thank you,
All right. Bye bye, CJ. Have a good evening.
Mr. Dennis. You
Bye
too.
bye. Okay, that's the end of the stream. So, um, yeah, you see these problems, they're not tricky because they're difficult. They're tricky because there is an easier way to solve the problem. But most of the time, students will try to solve it using just the formulas. So most of the tricky problems here were actually pretty easy once you know what to look for. Okay. Anyway, um yeah, we'll continue again tomorrow. So for anyone who'd like to watch the stream, yep, just join us and yeah, ask around. But of course, because this is not one of those open streams, we will again just go through what we need to go through with the students. In this case, CJ again will be our student tomorrow. Okay. When we do have our open sessions, and I will announce when there are open sessions, then yes, you can ask away and ask whatever you want to ask. Okay. All right. So with that, we'll end here. But before we do, do not forget to like, share, and subscribe to the social media platforms. And we'll just continue tomorrow. So with that, I bid you all again a good afternoon, good evening, good night, good day, good morning, wherever you are in the world, and stay freaky, everyone. Bye bye now.